en particular y de la conexión con la cosmología, entonces mucho a través del periodo de la inflación, entonces en particular el reheating. Y entonces, y mucho entonces sobre también la producción de materia oscura, que es algo que está bien no conocido todavía hoy en la cosmología física en particular. Y entonces, justamente hoy, Marcos nos va a hablar de uno de estas posibilidades, es el de Constraining Gravitationally Produced Dark Matter. Por favor. Sí. Bueno.
Nada, muchas gracias, Sebastián, por la introducción y la invitación. Me da mucho gusto estar aquí en persona. Ya había dado alguna plática antes, pero había sido virtual. Entonces, justo quise esta vez aprovechar y venir directamente, ¿no? Voy a cambiar a inglés nada más porque se me hace un poco más fácil. Entonces, espero que no haya problemas con eso. En fin. So yes, the title of the talk is precisely that one, Constraining Gravitationally Produced Dark Matter. I'm going to talk not about every possibility for gravitational production of dark matter. I'm going to mostly focus on scalar dark matter, okay, spin zero dark matter. Well, you will see one reference that I added there, which is a very nice review by Rocky Kolb and Andrew Long. If you're interested in more in higher spin or even more exotic scenarios, then you can have a look at that one. It's very recent, it's from last year. And I'm going to be discussing a broad range of topics. Most of the results that we have obtained have been done in collaboration with Matthias Beer, who's currently at DESI, and Jonas Werner, who's presently at Florida. He's going to move to Chicago in this year. Okay, very good. So, this being a colloquium, I think I need to introduce the topic from the beginning. So I'm going to be discussing scenarios in cosmology. Cosmology is this way that we study the universe essentially as a whole. And it is important to mention that our universe is quite peculiar, quite interesting, because it is not arbitrary. Actually, at the largest possible scales, which correspond roughly to spatial sizes larger than about the size of galactic clusters, it looks essentially the same. It seems to have the same properties, densities, and so on average at any point in space and in any direction that we observe. That is, at the largest scales, the universe is approximately spatially homogeneous and isotropic. And that means that we can essentially model the universe as a whole. We can take it and substitute it into Einstein's equations to study its dynamics, to look back in time, and of course, to make predictions. So, one way to do this is to choose a particular set of coordinates, which are called co-moving coordinates, which have the property that essentially matter on average is at rest in these coordinates. And with those coordinates, one can write the most general way for, the most general form for the metric of this homogeneous and isotropic universe. It is the celebrated Friedman, Lemaitre, Robinson, Walker metric, which is characterized precisely by these co-moving coordinates. This T is the cosmic time. This parameter K is a constant, and it encodes the spatial curvature of the universe. It can be positively curved, negatively curved, or flat, spatially flat. And in general, one can have a function here, which is called the scale factor. If this scale factor grows with time, then the universe expands spatially, and the distances between two objects grow with the time. They grow with a velocity that is proportional precisely to this separation. This is the very well-known Hubble's law. And precisely the parameter that relates linearly this velocity and this separation is the so-called Hubble parameter, which is given by the logarithmic derivative of the scale factor with respect to the cosmic time. So we can then write down this metric for the universe, and we can use it then, as I said, to substitute it into Einstein's equations. At the largest scales, the content of the universe, matter, radiation, and so on, are modeled as perfect fluids. So we can characterize the dynamics using an equation which is known as Friedman's equation that relates precisely the expansion rate of the universe, the Hubble parameter, with the energy content of the universe. So these rho i's are the energy densities of each of the components in the universe. These energy densities are not constant in general. for example, if we have non-relativistic matter, pressureless matter, then this energy density is going to decrease as the volume in which it is contained increases, which is the case in an expanding universe. So it goes down like the -3 power of the scale factor, while for radiation relativistic particles, we have an extra factor of this of A, precisely because of the Doppler redshift. Okay, so it loses energy faster. So that means that we can do a few things. For example, if we know the dynamics of our universe, we can map its components, okay? And we actually know its dynamics. We know, for example, that presently the universe is expanding at an accelerated rate. We can look back in time and draw this cartoon that is always present in these kinds of talks, where the universe is originated from this Big Bang. We still don't have a very good idea what the Big Bang is, but at the very least, it generates space-time itself and provides the initial conditions for this epoch of accelerated expansion, which is known, as cosmic inflation, after which the universe is populated with a primordial relativistic plasma in thermal equilibrium that will eventually give rise to the degrees of freedom that are present in the standard model. Then at much later times, it can originate the first atomic nuclei during primordial nucleosynthesis. And at even later times, it can give rise to the first neutral atoms during the recombination, which essentially is the moment when the universe becomes transparent to electromagnetic radiation. And therefore, it is the farthest we can see using light. And it generates then the so-called cosmic microwave background, okay? So with this information, then, as I said, we can map the energy density content of the universe. And as it is very well known, we know that essentially most of it here in this diagram at 68% is made of this very mysterious component, which is known as dark energy, which until a couple of weeks ago, we were very sure that it could be modeled with a cosmological constant. Now, we're not so sure, so I'm not going to go into the details, but there's a lot of it, okay? The component that I'm going to be focusing mostly on is dark matter. It's this 27% of the universe in this chart, which is essentially non-relativistic matter, pressureless matter, that does not interact electromagnetically with the visible sector, which makes only about 5% of the universe, okay? These percentages can essentially be extracted by looking at correlations in the cosmic microwave background. I'm not going to go into that direction, into those details, but so I'm going to focus mostly on dark matter and very early dynamics. So that's one evidence for dark matter. Of course, we know that there's plenty of other evidence, all of it gravitational so far. For example, very well-known fact that we kind of need dark matter to explain galaxy rotation curves. So galactic disks, seem to rotate, well, not seem, they rotate at a rate which is faster. They do it more rigidly than they should do it by just counting essentially the number of stars that we have in the periphery of them. So one way to fix this problem is to surround the galaxy with a halo of invisible non-relativistic matter. The other way we can detect matter indirectly is by looking at the deviation of geodesics with respect to lines. So that's gravitational lensing. In many scenarios, the amount of lensing that is measured does not coincide with the amount of matter that one can directly observe. Therefore, there should be some hidden matter. How do I say? Particularly, we can also use this lensing to map matter configurations in dynamical scenarios, such as the merger of galactic clusters. This is the bullet cluster, where astronomers can map the gas and the stars that make up these two clusters. This is essentially the merger of two clusters. One goes through the other one. So the pink is the visible stars and gas, which is heated up by the interaction and slowed down by this friction, essentially. But when you map the amount of matter by looking at what's behind the cluster, you get the blue blobs, which essentially tell you that most of the matter in the clusters is not interacting electromagnetically and is moving essentially freely. And of course, if we want to simulate numerically the universe from early times, we need to add dark matter as an initial condition. So anyway, that's some gravitational evidence for the existence of dark matter. Unfortunately, we don't really know what dark matter is. I mean, it could be a lot of things, from elementary particles to black holes, essentially. So there's a very, very, very wide range of masses and things that dark matter can be. I'm going to be mostly interested in, well, mostly, only the very last slide, I will say something about black holes. Interested in modeling dark matter as an elementary particle. And so if that's the case, it would be very nice to be able to detect it directly. That's the idea behind these direct detection experiments, where essentially we hope that dark matter particles can scatter off atomic nuclei of noble gases that are stored in these gigantic containers, and it can deposit some tiny amount of energy that can be detected by, well, the detectors. Problem is that despite the very rapid growth in efficiency of these experiments, we still don't have a smoking gun signal that can tell us that these processes are happening, so not direct detection. We can also assume that maybe dark matter does not interact very strongly with visible matter, but could interact sufficiently strongly with itself. And so it could self-annihilate in dense matter configurations, such as galactic nuclei, and give rise to, let's say, pair production. In this case, these are BB bar bounds from Fermi that could provide signals in the form of gamma rays or even neutrinos, which could in principle be detected, for instance, at ice cube. And again, we're lacking a smoking gun signal that can tell us that we know exactly what is the strength of these interactions. So might very well be that dark matter just doesn't like the standard model at all. Okay, it could be that dark matter completely ignores the three fundamental interactions that make up the standard model, and therefore only communicates with visible matter via gravity. Even in this nightmare scenario, we still need to do things. Okay, so maybe we cannot detect it directly. We can only get indirect information. But dark matter that only interacts gravitationally still gives rise to at least a couple of questions. The first question would be, how come there is a lot more dark matter than visible matter in the present universe? So can dark matter be produced as efficiently as it is required in the early universe only from gravitational interactions? The other question would be precisely what other kind of probes, indirect probes, most likely gravitational probes, we can consider in order to be able to tell whether or not these kind of scenarios are realized. Okay, so that's the purpose of the talk. Essentially, I will talk then first about production, and then I will focus on the limits after that. So if I want to talk about production, then I need to talk about initial conditions. As I mentioned a little bit earlier, the initial conditions for the universe are determined essentially after the Big Bang during inflation, this proposed epoch of accelerated expansion of the universe that in principle solves many of the initial condition problems of standard cosmology. I'm not going to talk about all of them, but we can talk very briefly about, for example, the horizon problem. The fact that since the age of the universe is finite, there is a horizon around a point or an observer, essentially. Okay, it's a causality radius that will be determined by the speed of light, of course, the age of the universe, but importantly as well by the expansion rate of the universe. So how fast the universe expands tell us how far away we can see and communicate. Okay. All right, so that's the horizon. Okay. So we can map this horizon into the farthest things that we can look at in the sky. So that would be, for example, the cosmic microwave background. That's very far away from us, not terribly far away from the scale of the horizon. Oh, the other thing, by the way, that's important is that during the standard cosmological expansion, that is matter or radiation domination, this horizon grows slowly, it grows linearly with time. And so that implies that if we look at two diametrically opposite points in the cosmic microwave background today, then if we go back in time, that would suggest then that those 2 points could not have been in causal contact with each other, and therefore they should be completely uncorrelated, including their temperatures. Okay, they should be in general different, which is not the case. What is observed is essentially that the whole sky, the whole CMB, is at the exact same temperature in one part of 10 in 10 to the minus 5. So that's a causality problem. That's the horizon problem. And of course, just using cartoons in an inflationary scenario, this problem is essentially trivially solved because before inflation, our whole universe could have fit in a tiny causally connected patch that was expanded exponentially fast during inflation. And so it would look like 2 points could not have been in causal. Okay, so that's more or less the idea. Now we have to go from pictures to equations, otherwise we're not doing physics. And turns out that describing the dynamics during inflation is not that complicated. Arguably, probably the simplest way to drive inflation is to assume the existence of a singlet scalar field that I'm going to be denoting by phi, and which was jokingly called the inflaton initially, so now it's the inflaton then, which comes equipped with sufficiently flat potential. In this case, it is flat at large values of the field, and the field can begin at sufficiently far away from this minimum. Okay, this example that I'm showing is the one that I'm going to be using for definiteness during the talk. Is the celebrated T model of inflation of Kalosh and Linde, already more than 10 years old, which is a hyperbolic tangent square. Okay, so if these conditions are met and the inflaton can begin rolling down the hill towards the minimum, one can show that the metric of the universe takes very quickly the standard Friedman-Robertson-Walker form with k equals to 0, a flat, it leads to a flat space. And the background dynamics can be described very easily. All the gradients go away. And so the Klein-Gordon equation in the expanding universe that this field satisfies can be written in this form. It's a very simple form because it's essentially Newton's second law, right? It's just an acceleration term. It's a force term coming from the derivative of the potential. And there is a friction term, which is proportional to the Hubble parameter that has to be connected precisely with the energy density of the field itself. At this background level, the energy density is given by the sum of the kinetic and potential energies of the field, and the pressure density can be shown to be the difference between them. So solving this system of equations up here in the plateau is the simplest thing in the world, because up in the plateau, the kinetic energy is negligible. There is a very small gradient, and also there is friction. So most of the energy density is the potential, which is approximately constant. And just by following these equalities, the Hubble parameter is also approximately a constant, implying that the solution of this differential equation is a growing exponential. That's inflation. Okay, the field will very slowly roll down the hill until it reaches the minimum. At that point, inflation ends, and the universe enters the reheating epoch, during which the inflaton starts to coherently oscillate about the minimum with a decreasing amplitude, and the energy stored in these coherent oscillations is transferred into standard model degrees of freedom, and why not dark matter as well. Okay, so those are background dynamics. Those are very simple. We like inflation a lot as well, because it not only leads to the spatially flat, homogeneous, and isotropic universe that we know and love, but it also provides a causal way to generate the primordial fluctuations that we can also measure in the sky. Okay, these fluctuations are truly primordial. They come from the quantum fluctuations in the scalar field and in the metric, which are also stretched very efficiently by the expansion. Turns out that during inflation, the size of the causality radius doesn't change too much, but the physical wavelengths of these quantum fluctuations will be stretched together with space as the accelerated expansion goes on. For certain values of the wavelengths, it can happen that during inflation, even if the fluctuation starts with a wavelength that is much smaller than the size of the horizon, eventually this wavelength will become as big as the horizon or even bigger. Okay, we call this moment the moment of horizon exit. And that means that after this point in time, this fluctuation is going to be out of causal contact with itself and with the rest of the universe. It will, for a certain gauge invariant combinations that I will mention in a second, it can remain then frozen, constant, and it will not evolve at all until much later times when the size of the horizon eventually catches up with the fluctuation during horizon reentry. These are co-moving coordinates. So here you have to divide by the scale factor, meaning that the size of the horizon is shrinking during inflation and then it grows after inflation, and the wavelengths are constant. So the fluctuation is inside the horizon, exits the horizon, it's outside the horizon, and then it re-enters. For single field models of inflation, there are essentially two fluctuations that will be excited by the accelerated expansion. The first one corresponds to a scalar fluctuation. One can associate it with the curvature perturbation. This curvature perturbation is a linear combination of the metric and the field fluctuations, and it is usually characterized in terms of its power spectrum, which is defined from its two-point correlation function in Fourier space. Let me not go into a lot of the details. One very, very, very nice thing is that this power spectrum can be reconstructed from observations of large-scale structure and the cosmic microwave background. This is the Planck reconstruction of the power spectrum around the so-called Planck pivot scale, which is about 0.05 inverse megaparsecs. The constraints are very good. The red are the uncertainties. And this plot is precisely showing that the measured power spectrum is approximately scale invariant. It's very flat, but it has a slight tilt, a slight slope in this log-log scale. Okay. From the inflationary theory, it is actually a very simple exercise to predict that that's precisely what you should obtain. In fact, predicting the value of this scalar tilt is the easiest computation that you can do in physics, probably. The only thing you need to know is to take 1 and 2 derivatives. That's it. So you can predict the value of that quantity. The other set of fluctuations that is excited by accelerated expansion are the tensor fluctuations, primordial gravitational waves, which can also be characterized by their power spectrum. Here, the phenomenologically relevant quantity turns out to be the ratio between the tensors to the scalar, the tensor to scalar ratio. Okay, so these are the quantities that we would like very much to measure and to connect with our inflationary models. And we can do that very easily because the fluctuations don't evolve at all in the middle. So that's it doesn't require then too much thought. The problem is that in order to connect this point and this one, we need to know the expansion history of the universe between the 2 points. And that implies, in particular, we need to understand what reheating is doing. And so I usually like to bring this point up always, despite the fact that I'm supposed to be talking about dark matter, because this reheating represents then probably the main theoretical uncertainty for a given inflation model. This uncertainty is usually characterized in terms of what is known as the number of e-folds of that particular fluctuation. So this n is just the natural logarithm of the scale factor, and it is defined as the separation between horizon exit and the end of inflation. This number of e-folds depends on the duration of reheating and the amount that the energy density of the universe is diluted during this epoch. Let me not go too much in details, but just show one example. So for the T model that I was showing previously, one can compare, the predictions with the observational constraints. Here I'm using the Planck and Bicep combined results from 4 years ago. I'm not touching the ACT results yet. So this is NS and R. This is the 1 sigma and 2 sigma contours. R hasn't been measured yet. That has to be said. And this dumbbell shows precisely the predictions, let's say, from the T model. If reheating doesn't last any time at all, and the dissipation of the inflaton energy into radiation is instantaneous, then you get a very high initial temperature of the radiation-dominated era, 10 to the 15 GeV, and you are perfectly within the observational contours. However, if reheating lasts as long as it can last, all the way down to primordial nucleosynthesis, then you get this point, which is very outside of the observation. Okay, so one has to really be able to model reheating to connect well, a model with observations. Okay, I need to say a little bit more about reheating because that will bring me finally to the dark matter production problem. So, as I mentioned earlier, reheating begins when inflation ends. The universe ceases to grow in an accelerated fashion. And the nature of these oscillations and the expansion rate of the universe during reheating will be determined mostly by the shape of the potential, the scalar potential of phi, around the minimum. Okay. I'm not going to talk about all the generalities. That would require a completely different talk. So let me just mention very briefly what happens for the T model potential that I showed earlier. For that potential and a lot of a very, very big class of potentials, this minimum can be approximated as a parabola. It's quadratic. And that means that the dynamics can be described in a very simple terms because essentially the motion of phi is damped harmonic motion. In fact, you can write the solution as the product of a decaying envelope and a periodic function that in this case is nothing but a trigonometric function to obtain the, yes. Yeah, here it's just the H. I will mention what happens when you add the DC field. Yes. So, okay, if we want to obtain the expansion rate, then we average over the oscillations. This leads to a virial-like relation between the kinetic and potential energies that immediately implies that the mean pressure density of the field is approximately 0, meaning that this coherent oscillation of the field mimics a universe that is filled with non-relativistic matter. Okay, so going back to the question, this ignores everything related to the rest of the universe. This is only the inflaton. Now, during reheating, we need to populate, we need to create all of the standard model degrees of freedom. For those, because I want to talk about non-trivial dynamics of dark matter, I am going to assume that the reheating process is very simple. What does simple means? This is essentially what is generically called perturbative reheating, which means a lot of things. Okay, the first and most important thing that it means is that throughout the reheating process, we can always, at all times, continue talking about a spatially homogeneous, coherent inflaton field. Okay, so this field is going to be losing energy into particles, but it's still going to be an oscillating field. So the only thing we're going to see is a decrease in the amplitude of the oscillation. That doesn't have to happen, but for the purpose of this talk, that's what I want to say. The other thing is that the couplings of the inflaton to the standard model degrees of freedom are sufficiently small so that we can ignore any resonant effects in the production of the modes. Okay, I will mention that later, but essentially we're far away from saturating the phase-space distributions for fermions that would lead to Pauli suppression or to producing Bose-Einstein condensates essentially in the decay products for Bose. So if those conditions are met, we have weak couplings and we have a coherently oscillating inflaton field, then we can also model reheating just by looking at the background dynamics. Okay, we model it as the energy exchange between two ideal fluids, one made of the inflaton, the other one made of the primordial radiation. And phenomenologically, you just stick a decay rate into the equation of motion as an extra dissipative term. I'm not showing that here, but using the Boltzmann equation, you can check that arriving to this continuity equation by averaging this equation, or by actually writing down the Boltzmann equation and doing all the math, you get the same equation. So that's okay. This continuity equation tells us basically that the energy density is lost due to expansion and due to decays. By energy momentum conservation, whatever you lose in the inflaton, you gain it in the radiation. And this gives a set of two coupled equations plus the Friedmann equation that are very simple to solve, even by hand or numerically. Okay, this is one example. So one way to avoid strong resonant effects is to assume that the inflaton decays into a pair of fermions with a coupling, a Yukawa coupling that is sufficiently small for quadratic potential. Sufficiently means 10⁻⁵ or smaller. And since these are relativistic, then the decay rate is nothing but this expression, the usual QFT expression. Oh, by the way, that's the other thing it means. The perturbative reheating means that we can use Feynman diagrams. So we get y squared times m. This is a constant, so we go back to the set of equations, we plug in that gamma, and then we can obtain the evolution of the energy densities during reheating. So we recover the fact that the energy density of the inflaton redshifts like matter. At the beginning of reheating, very quickly, the primordial plasma is populated to a maximum value, and then the energy density decreases at a rate that is determined by the competition between particle production and dilution from expansion. These two curves, just from their slopes, essentially, will always meet at this point, which signals the end of reheating, the beginning of radiation domination. And at that moment in time, for instance, we can define the reheating temperature. That's the initial condition of the radiation dominated air. Okay, so these are generalities for essentially any model of inflation that at the very least give rise to the standard model degrees of freedom. I don't want to talk about that too much, although it's inevitable to talk about it. I want to discuss mostly where is dark matter coming. Okay, so I am going to make a slightly more general assumption here than what I said at the beginning. I am going to assume that we have a scalar sector. Okay, so we have a spin zero particle that I'm going to be denoting by chi, but I am not necessarily going to call it dark matter until it is necessary. Okay, so I'm just going to call it a spectator field. What does spectator mean? It means that it does not dominate the energy budget of the universe at early times, at least. Okay. The main assumption that we have to make is to segregate it from the standard model. So there's not going to be, there are not going to be any couplings between this chi and the standard model. The only thing we can, that's one thing. The other thing I'm going to assume as well, at least for the purposes of this talk, is that chi is also not going to interact with itself. Okay, so the only thing I can write down in my Lagrangian then is a kinetic term, a mass term, because it has to be massive, otherwise it will not be able to be dark matter. But I can do a couple of things that are essentially necessary if I'm looking at the radiated corrections that can arise if I only write these two pieces here. I am forbidding chi to talk to the standard model, but nothing forbids me for coupling chi to the inflaton. Okay, so chi can be coupled to the inflaton. I am at times going to turn on that coupling, at times I'm going to turn it off. Okay, that coupling is going to be called sigma. And the other thing that I have to do inevitably is to couple it directly to the Ricci scalar, to the curvature, even if. Yes. Yeah, that's what I was going to say. Yeah, that's what I was going to say. So, I mean, I'm not coupling them directly inside of the what I'm calling the Lagrangian, but whether I like it or not, there's a G here, and I can also couple it to the curvature. So, but it's still gravitational, so that's the point. It's talking gravitationally to the standard model, not directly. And by direct, I mean SU3, SU2, U1. Yes. Here sigma can be, well, okay, I can, at the bare level, it's just a constant. If I want to run it with energies, then yes, I mean, it has to run it. Sigma doesn't have any units here. Chi has units, yes. It's a scalar field. It has dimension 1. So we have 2, 4. Yeah. Yes. Anyway, I'm not going to say too much about this non-minimal coupling. I will just say some things about it. Turns out that talking about this guy or this guy are very similar. Okay. Anyway, that's going to be the setup that I'm going to be considering. Again, perturbative reheating. And then I'm going to take the T model. So the couplings that one needs to keep in mind are this sigma, this lambda, and this psi. As I said at the beginning, I'm just doing this for a scalar. If you don't like scalars and you want to consider a spin 2 dark matter particle, then you can do it. That's not a problem. But things become very quickly very complicated. So this review, which as I said is 1 year old, is very nice. So you should have a look at it if you're interested in the topic. Anyway, now that I have an action, a Lagrangian, then I can do a couple of things. I can think directly as a particle physicist and start drawing Feynman diagrams and do computations. Or I can be a little bit more careful, because it turns out that this setup, despite the fact that it's, in my opinion, so simple, still has a lot of complications. So the best thing one can do, I think, is to take this Lagrangian and then just compute the equations of motion and see what comes about, okay? So we can either take the variation of this Lagrangian directly, or we can be a little bit smarter because of experience and introduce a new set of, a new set of variables. So a new time coordinate, which is the conformal time, where we essentially factor out the expansion of the universe. And then same thing for the scalar field. We factor out the expansion and we define a new field X. If we do that, we replace that in the action and then we compute the equation of motion. We obtain something that looks very much like the Klein-Gordon equation for X in flat space-time, except that there is a time dependence in what would be the master. There is a time dependence from the scale factor there, but most importantly, this effective mass also carries a time dependence from the coupling to the inflaton, because the inflaton is evolving with time, and also from the Ricci scalar. Even if I shut off this coupling, that R is there. The only way to make it go away is to make psi equal to 1/6. Okay, which would be conformal coupling. All right, so I can write this equation of motion. Of course, this has to be a quantum field, so I'm going to quantize canonically as a superposition of oscillators. I introduce the Fourier transform and a set of, well, an infinite set of creation annihilation operators that defines the mode functions of the field X. And for those, I can get the corresponding equation of motion, which looks very innocent. It's just an oscillator-like equation with an effective frequency that inherits the time dependence from the effective master. Okay, so from here, we can discuss how good it is or not to assume that perturbative dynamics are applicable here. They are going to be certainly applicable when I consider very short wavelengths, okay? That is sufficiently large values of K. How large I have to make them? I have to make them so large so that these quantum fluctuations of the field never leave the horizon during inflation. Okay, so those modes always exist. I mean, K goes from 0 to infinity. For these modes that never leave the horizon, and sigma couplings that are small. Okay, I will say what small means in a bit. Okay, I can essentially treat this problem perturbatively. Okay, the biggest contribution to the effective frequency is just the K-squared term, which is the free particle, and everything else can be seen as interactions. So I can either start working directly with this equation of motion, or I can equivalently say, okay, the interaction picture applies here, and I can just do the regular things that I do in quantum field theory, which is drawing Feynman diagrams. The relevant Feynman diagrams here for the production of chi particles are going to be active during reheating, as they should be, and correspond to these two. So I have a pair, I have an annihilation of inflatons that give rise to the production of two chi particles, in this case from the exchange of gravitons. So that's the gravitational production. If I allow for the direct coupling between the inflaton and chi, then I will also have this contact term. So what do I do with these two Feynman diagrams? The usual thing, I compute the amplitude and I square it. Okay, so that gives me the square amplitude for the process. Since this coupling talks to the energy momentum tensor of the inflaton, the lambda coupling that was in the inflaton potential appears in here. Okay, so in reality, the real effective coupling that controls the production is not sigma, but it's sigma divided by lambda. So that's going to show up everywhere. Weak coupling means sigma divided by lambda smaller than 1. So that allows for these to apply for sub-horizon scales, and psi is there. what do I do with this amplitude? I'm not going to go into the details of the Boltzmann equations, but that's what you do. You take it, you substitute it into the Boltzmann equation, and this Boltzmann equation can be solved analytically, and it predicts a phase-space distribution that has a power law form, okay? These are very weak couplings, which means that we don't have thermal equilibrium in the system. All right, so this is good, this is easy, but it is incomplete. That's the problem. Why? Because we also need to consider modes that can leave the horizon during inflation. And for those, it is instructive to, instead of writing the effective frequency in terms of the Ricci scalar, to rewrite the Ricci scalar in terms of the Hubble parameter during. So what I can do is to factor out R essentially from here, which turns out to be just 2 times AH squared. And I get this expression between the brackets. Modes that leave the horizon are modes where the wavelength was larger than the causality radius, which is equivalent to having K much smaller than A times H. And so that means that in this effective frequency, this term is going to be bigger than this one. Okay, what is the problem? The problem is that if my mass is not sufficiently large, that is, if it is smaller than the Hubble parameter, essentially, or if my coupling to the inflaton is not sufficiently large, that is, this ratio sigma over lambda is smaller than 1, or if my coupling to the curvature is not sufficiently large, it's smaller than the conformal one, then the term that wins in these square brackets is this minus 1, okay? Which makes the effective frequency negative. The effective frequency is squared negative, signaling this tachyonic instability. Essentially, this no longer looks like an oscillatory solution, but it's an exponentially growing and decreasing solution. In pictures, that looks more or less like this. So upon horizon exit, not only the wavelength is stretched, but also the amplitude is growing. And it's going to continue growing until inflation ends. And eventually, this mode will re-enter the horizon at much later times during reheating or radiation domination. And if I compare only this initial state with the final one, it's going to look like particle production, okay? But we're not really looking at decay processes. We're looking at these field dynamics. So we cannot use the perturbative picture, okay? What we really need to do is to directly solve the equations of motion. Now, this is a very old problem. I'm putting here the Parker and Ford papers, Parker from the 60s, but historically, it is very well known that even Schrödinger noticed that this was the case, okay? It's a very old problem, and there's been a lot of work in the literature to understand this process analytically. During inflation, one can actually use the slow roll formalism to approximate the solution for this equation of motion. Looks a little bit horrible, but okay, that's not a problem. And from that, you can predict what has to be the tilt of the phase-space distribution. But predicting the amplitude is not straightforward because you have to take into account the smooth transition between inflation and reheating and then to radiation domination and so on. So just give the problem to the computer and the computer solves it. That's probably an easier thing to do. So what I'm showing here is precisely the form of the phase-space distribution. I'm ignoring the non-minimal coupling, but if you turn it on, it looks essentially the same. For a weak inflaton coupling, that is sigma over lambda is smaller than 1. I'm using a new set of variables. So this Q is the comoving momentum normalized to the mass of the inflaton for convenience, because that allows me to separate the distribution into 2 parts. The piece that is produced perturbatively during reheating and the piece that is produced non-perturbatively due to this exponential growth during inflation. If I have very weak coupling that is pure gravitational production, then my phase-space distribution looks like the red one. It is very tilted to the infrared, and of course, it predicts what should happen. Well, not predicts, it tells us that what our intuition was correct. The modes that leave the horizon the earliest are the ones that grow the most. Okay, so most of the dark matter then is produced at the beginning of inflation, making it the oldest possible thing that exists in the universe. I can kill off the tachyonic instability if I make the coupling to the inflaton bigger. until essentially my distribution is only peaked at the central value of 1, which is saying that dark matter is produced at the beginning of reheating, still making it the oldest thing. Okay. We have the phase space distribution. Yes. I'm going there. Yes. Yes. So that's production. Very good. So attending to the question, now we have to worry whether or not this makes sense considering fluctuations and observations in this. So, but again, we have the phase space distribution, so we can do a lot of things. Which is the first limit that first constraint that we have to consider? Well, the one that we know, 25% of the universe has to be made of dark matter, 27. Okay, so we have to be able to saturate the relic abundance by these gravitational production. This energy density fraction, omega, can actually be related in the variables that I introduced in the previous slide with the mass of the field and the reheating temperature times the integral of these dimensionless phase space distribution that I'm showing. For very small couplings, that is pure gravitational production, this integral scales like the inverse of the mass, meaning that this mass and this mass cancel, and my relic abundance depends on one single parameter, which is the reheating temperature, meaning that there is one and only one reheating temperature that can predict the observed dark matter relic abundance. It turns out to be about 27 GeV, if I'm not mistaken, 30-ish GeV. So if you have a higher reheating temperature, you overproduce dark matter. If you have a smaller one, you underproduce it. So first answer to the questions is yes, you can fill the universe with dark matter only from gravitational interaction. This scaling breaks down when your mass is sufficiently big. Okay, you can kill the tachyonic instability by also considering super heavy dark matter. That's what's known as Wimp-Silas, Rockian collaborators. So I'm not going to go too deep into that scenario, but you see that it bends off. You can cover the rest of the parameter space for a wide variety of reheating temperatures if you play with the coupling to the inflaton. So that's possible. Then you can have all of the dark matter coming from these dynamics. We need to be able to answer other kinds of questions, consider other kinds of constraints. For example, structure formation. So as I mentioned before, this dark matter production process is a non-thermal process, and so you have to worry about whether or not dark matter will be sufficiently non-relativistic when a structure formation occurs. Okay, if dark matter moves sufficiently fast, then it might not be captured by shallow gravitational wells, and that will lead to underproduction of small structures, which in this case is illustrated for warm dark matter. That's dark matter producing thermal equilibrium, but which is very light, which gives rise to very smooth structures compared to the grainy ones for pure cold dark matter. These constraints, from the very little that I know, can be obtained, for example, from observations of the Lyman-alpha forest at small scales, which in just drawings is essentially saying that we can measure the distribution of matter at subgalactic scales by looking at light emitted very far away from us, and as it makes its way through these clouds, essentially, it would lead to this forest of emission and absorption lines in the hydrogen. Okay, by looking at those, one can characterize the shape of the matter power spectrum at small scales, and since we don't see a suppression at these scales, that means that dark matter has to be sufficiently non-relativistic. For warm dark matter, that implies that the mass has to be larger than about 3 keV, roughly. For non-thermal production scenarios, this does not apply because this one is purely thermal result, but you can devise ways to connect this bound with a generic bound for any out of equilibrium scenario. I'm not going to talk about this because in our case, it's more or less obvious. For pure gravitational production, most of the dark matter is produced extremely early, which means that it has the entirety of inflation, reheating, and radiation to redshift a lot, even if it is light. And so this bound, instead of being 3 keV, goes all the way down to 10 to the minus 25 or so GeV. So we can have ultra light dark matter as it is usually considered for scaling fields. So this is also consistent with that, except that here we're not assuming a vacuum expectation value. Everything is quantum fluctuation. So that is okay. You get some exclusion from Lyman-alpha. The most interesting one might be probably isocurvature before the gravitational waves, of course. What is isocurvature? Well, as Sebastian was pointing out, for single field inflationary models, as I mentioned at the beginning, there is only one scalar fluctuation that is excited by the expansion, the curvature perturbation, meaning that every other scalar perturbation that we see in the universe today, that is sufficiently perturbative, of course, comes from it. And so all of the energy density, all of the fluctuations in the energy densities of the components of the universe are correlated. They're in phase, essentially. So they satisfy this constraint. The relative entropy is vanishing, and that gives the name adiabatic. But essentially, in pictures, that tell us essentially that if we have an overdensity of visible matter in one region of space, we should expect an overdensity of neutrinos, of dark matter, and of every other thing that exists in the universe in there. In the gravitational production scenario, we don't really have one single dynamical field during inflation. We have two. We have the phi field and we have the chi field. So if I think, for example, then that chi is going to become dark matter, then the density fluctuations for dark matter are not necessarily going to be the same ones as for the rest of the universe. The relative entropies don't vanish anymore, and these are called isocurvature, which I still don't know where the name is coming from. For me, it's just not curvature, but I don't know why iso. So anyway, you can produce not curvature perturbations. These not curvature perturbations, in principle, are detectable in the cosmic microwave background. How? I don't know, sorry, but in principle, they are. And so they have not been detected yet. The best we have are constraints relative to the curvature perturbation. So if these isocurvatures exist, they can be at most a few % of the curvature perturbation. These constraints importantly apply only at large scales, at CMB scales. At smaller scales, nobody knows, which is good. Well, okay. Before the good, the ugly. How do you compute isocurvature for this scenario? It's a nightmare. Why? Because the isocurvature is related precisely with the correlations of the energy density fluctuations. But in this scenario, these energy densities are quadratic in the fields. So this is really a 4-point correlation function. And the problem is not computing it. That's very easy. The problem is the fact that you're playing with quantum fields. And so you have to do regularization and renormalization. That's the problem. You can regularize these ugly integrals by using normal ordering, as you do in regular QFT. But the price to pay is that you have to integrate this horrendous expression. Okay. Turns out to be that it's possible. You can even animate it. Let's see. This is the isocurvature. There's going to be a straight, a very vertical line. I will address it in a minute. But this is more or less how the isocurvature is being generated during inflation. This is the number of equals with respect to the end of inflation. And then during reheating. So it oscillates a little bit, and then it stays constant. Okay. So this isocurvature can be measured. Why I added this animation, the important thing that I need from the animation is the fact that the isocurvature is evolving rigidly. It's only doing this. It's not getting deformed. That's important. If we plot it at the end of the dynamics, it looks more or less like this for a given coupling. I will address the shape in a minute. There was this line that seemed to be blowing up, and that leads to ultraviolet problems. That's an artifact of the regularization. So the integral is regular, but it hasn't been renormalized. So that's work in progress still. But anyway, if I play with the coupling, for example, I can see the following spectra. If I have very weak couplings, that is gravitational production, I see something very similar to the curvature perturbation, an almost scale invariant spectrum of isocurvatures in this case. The problem is that the amplitude of the spectrum is huge. In this case, it goes to 10 to minus 2. So this means that the Planck constraints are essentially ruling out pure gravitational production for light dark matter, okay, like scalar dark matter. In order to make it compatible with observations, you either have to make this coupling larger than about 0.02, or you have to make the mass of the dark matter particle very large, about 0.5 times the Hubble parameter at the end of inflation, which is about the mass of the inflaton. So think 10 to 12 GeV or so, or the coupling to the curvature very, very strong. Okay. Why was I saying that it was a good thing that we don't have constraints on night? Well, good and bad thing. It's a bad thing because we don't have constraints here. Good thing because that doesn't kill the model. Okay, so we need to kill it using different things. So that was for coupling to the inflaton. This is pure gravitational production. So if you play with the mass of the particle, then you can be consistent with isocurvature constraints, and that adds an extra bit in here. Okay, so still some parameter space to play with, including a tiny bit in here that it's almost not visible for tensor graph. I am almost done because what follows is very complicated. So here's the isocurvature power spectrum. Okay, the isocurvature power spectrum, as I mentioned, is made up of these density fluctuations. But of course, if you have large density fluctuations, in this case in the form of scalar fields, you can source other things. In particular, you can source gravitational waves. Okay, so these gravitational waves would be different from the primordial gravitational waves coming from inflation. Those are just the vacuum state being stretched out by expansion. These ones are being sourced by the continuous production of the continuous excitation of the spectator field chi. Okay, so this source shows up at second order in perturbation theory on the right hand side of the equation of motion for the tensor modes, and solving it is a bit of a mess. Okay, because you have contributions from the Newtonian potential and the field itself. So you have to solve first Poisson's equation in terms of the field. Then you have to take the tensor modes, decompose them in Fourier modes, and then solve this equation of motion in principle in terms of a Green's function, for example. Then you have to take the solution, square it to compute the power spectrum, and then with it, you can compute the amount of gravitational waves that you have. Okay. The only thing I'm going to say about the math is the fact that since the isocurvature power, okay, turns out that these gravitational waves then can be shown to be directly sourced precisely by the isocurvature. Okay, so these are isocurvature produced gravitational waves. The computation simplifies because the dynamics of the isocurvature power spectrum is rigid. So you can essentially factor the time dependence from the scale dependence. And that leads to some complicated but doable integrals that I don't want to talk about details, that allow you to compute this gravitational wave density as a function of the frequency if you play with the parameters of the theory, and you can compare them to existing and hopefully upcoming gravitational wave experiments and observatories. Okay, so LIGO is all the way up here. The main things, okay? So this will be LISA, this is DBO, DESIGO, here the dragons, I don't want to talk about that. Here the CMB non-observation of gravitational waves, so that's Planck. This hopefully will be Lightbird. And up there we have the delta and effective constraint. We cannot saturate the universe with gravitational waves. Okay, well, it turns out that if you produce you can produce a lot of gravitational waves from gravitational particle production. Okay, when you produce a lot of them, turns out that you also produce them with a red tilt, which is a little bit weird, but okay, that's what you get. So let me just flash some of the results very quickly, and then we can discuss them later because I don't want to take more of your time. For example, what I'm showing here is the corresponding spectrum of gravitational That's a good question. I don't remember if. Okay, okay. Yeah. Yeah, it was noise, but sorry, yeah, noise, dust, yes. But I don't remember I was. Yeah. Okay. Blue tint. Okay, I see. Well, I'm saying weird because we were quite biased by earlier papers. Yes. Yeah. Okay. Okay. So I need to think a bit. I need to think. But okay, very quickly because I don't want to waste your time anyway. What am I showing here? I'm showing let me think. A spectator field that is not necessarily dark matter. Okay, so this spectator field is allowed to decay after it's been produced. Here, I am allowing it to decay as late as possible, right before matter radiation equality, except for this line here, which would correspond to dark matter. Okay, so I play with the reheating temperatures by fixing the mass and the coupling, and that shows me that I can improve my constraints in the model simply because these tensor modes I have been, well, okay, simply because these tensor modes are incompatible with large-scale observations. You can also fix the reheating temperature and play with the coupling, making these fields vary with this coupling. Actually, the sensitivity is, well, high, okay? And this is essentially the curve that we were looking for, more or less, right? It's not incompatible with CMB, but you might be able to see it with some other probe. If you consider that chi field is really dark matter, then you can put constraints from this gravitational wave emission, precisely as I mentioned from CMB probes. And these constraints are a little bit stronger than the isocurvature ones. If isocurvature required this coupling to be larger than 0.2, so maybe a little bit stronger. Not too much, but a bit. You can also consider pure gravitational production and then constrain the mass of the field or the mass of the field. I think I did the same thing here. I don't know why. This is unstable. This is stable, dark matter. You can also use gravitational waves as a probe. Last slide that I have. Oh, yeah, yeah. Well, these are the spectra. And yes, so as in terms of omega, as a function of the frequency. So if you're talking about the dimensionless tensor spectrum, then yes, we have them. It's just I'm not showing them here. So, yes. Yes, we do have them. I don't remember. I don't remember that because this is. Yeah. This is still a lot work in progress. So everything is hidden in the code. We need to take it out. But yes, everything is in there. Anyway, main take-out message is essentially you can use gravitational waves to also put constraints in these scenarios. Also, since you produce a lot of density fluctuations, why not think about producing primordial black holes as well? What's the answer? I have no idea. So, why? Because then the distribution that the overdensities follow is not Gaussian. You cannot use projector or anything else. You have to do numerical simulations. Yes. So that's why I don't know. Yes. Right. Thank you.
Time for a few questions. Okay, I can start with one because it's exactly different because you can have some prediction of this isocurvature gravitational but very high frequency.
Mhm.
So here you have the possibility to use this black holes. Because something that we do is to try to see which kind of amounts of black holes we can do to solve the problem with other supermassive black holes.
Right. Yes. So here precisely that's more or less the goal, to look at the exact, let's say, shape of the PDH
Without presence.
but without presence. Yes.
That's a really
So you have to be a little bit careful, because here it depends on when the modes are re-entering. So the highest peak is re-entering during reheating, which is matter dominated. And so you have to also keep that in mind, that some of them re-enter during matter, some re-enter during radiation. Besides the fact that, of course, non-Gaussianities and so on. But yeah, you have to be a little bit careful. I'm not super optimistic about the amount that you might get, because the isocurvature is very large, but the density of the field itself compared to the background is small. So, yeah.
I think I got lost at some point.
That's it.
Degree of freedom.
Yes. But I can allow it to decay. So for the most of the talk, I was assuming it was dark matter, stable, and nothing weird about it. Just for generality and for comparison with previous literature, which is quite recent, we're also allowing it to be unstable, simply because that's related with these curvaton and so on scenarios. It would lead to particles, yes. Yeah. Yeah. Yeah, in that case, it cannot be gotten. Yeah. So that's why I was making a distinction, not very strong one here. This one was blue, and I'm just calling it spectator. This one is where I'm calling it dark matter. So here it's stable, here it's unstable, so it's something else. It only leads an imprint in the form of these gravitational waves, for example.
Okay, at the beginning you said that dark matter.
Yeah, I know. So
Larger than the organic.
yeah, exactly. I thought that this would be
similar. That's very important.
yeah. I
5 to 1.
Yeah.
It's not 10 to 5
Yes.
to 1.
Yes.
We don't know why.
Yes. So coincidence we're not addressing here, if that's the question. Yes.
Thank you. Last question. I think your question for you.
Yeah, it can be. Yes.
Okay, so if there is no, so please 5 seconds.